property, and the goal is to have the slope larger than 1, the absolute value larger than 1. Make sense?
Yes, Professor.
Okay, great. Okay, any question, just stop me, right? So there are other matrix we need to know about the logic, right? We always take it for granted, but now you are at this level, you need to be aware of that, because that is going to hurt your design when at the end, if you don't consider well. Is this a unidirectional? Unidirectional means that the signal can only pass from in one place to the other, right? This is unidirectional. Signal only go from left to right. If I draw this to you, is this unidirectional? This is an inverter.
Yes,
it is, right? Yeah, because the input determines the output. If input is 0, output is 1, output 0, input 0, output 1. Or if you put output 0 or 1, you are not going to affect my input. Well, the symbol is that, but how about the real implementation? Well, that depends on how you implement. If I implement it with a CMOS logic, is this unidirectional? Well, I have a capacitor from the gate to the source, CG, to the drain. This is to the drain, right? CGD. For both the NMOS and PMOS. I don't draw it well. It's time. Right? So the signal can couple back. Okay, so you take it for granted. You always think that logic only go from one way. Now, in reality, it is not. Is there a problem? Usually it is not. But let's say you try to push your design to a limit, and you do not do the enough simulation with by including the capacitor. You just do a high-level functional. You just show, oh, we have a deadline tomorrow. Oh, let me just do a quick logic synthesis. I come up with a new great idea, save a lot of area, and also much faster. And you show your boss, but we don't have time to do more verification, do the full chip simulation. Let's tape it out. And then you will be doomed to fail. Because you did not do the simulation, actually, there will be backward coupling. I don't know how complicated your circuit is. You introduce something new, but you forgot about this backward coupling. You actually screw up the whole logic, right? So usually, we are not going to deal with this more in this class. We will deal with it a little bit later, but I hope that you know that underline is that it's not as ideal as what you think about, okay? So yes, it's unidirectional, but depends on what situation, okay? Yeah. Now, how about fan out? You know what is fan out? Fan out is how many gates I'm driving, how many equivalent gates I'm driving, right? So what is the issue of having a very large fan out? Anyone can tell me?
The driving voltage decreases as we progress through the circuit.
Okay, that is good. But what if this is a CMOS circuit, right? Let's say I have why the voltage will decrease if it is a CMOS circuit. Right, so ideally, if you bring this to an undergraduate who just started the digital circuits class, that student will say, why don't I just have a very large fan out and then it's done? Why you guys synthesize the tree logic and also make the delay so long? Why don't you just drive 100 inverter?
Is it because of low capacitance?
The low capacitance. Yes, you have larger capacitance. Then someone may even ask you more, why capacitance is a problem? Why larger capacitance is a problem?
Because it needs more time to charge the capacitor.
Why I need more time to charge the capacitor?
So as the current through the inverter reaches a saturation current, if the inverter has some limit, then it will take some time.
Okay, you have another view, right? So he's saying that the current is limited. That's very good, right? So he already see that this is not just a triangle. This is actually a transistor. And when it is on, let's say when this is 0 volt, this is off, this is VDD, and I'm relying this guy to charge N times CG. I should assume just CG, right? CGS. I'm relying on this to charge them. And this is limited to the ID set. So it takes time to charge, right? What if it is not limited by ID set? If you see even deeper, this guy itself is also a resistor. It's not a perfect current source, right? So ID set limiter, right? And then PMOS has resistor, RP. So then you have an RC delay, right? So I was trying to fish for this answer, RC delay, but your classmate is even better. He thought about, even you don't have RC delay, my transistor have a limited driving capability, right? You won't see this by this symbol, right? We always work on this symbol, but we need to think deeper. How about fan in? Okay, you say I cannot drive other person. That's okay. But what if many people drive me? And what is the problem again? Many people drive me. Why I cannot have very large fan in? Any idea? It might be difficult, but
could it cause you to miss timing?
it's the
Timing issue?
But why there's a timing issue? It's timing issue. You're right. Why?
Because like some signal travel to the gate fast, the gate slower, then you have glitches.
Yeah.
I mean, you cannot guarantee that all the signals are right at the same time as the input port.
Okay, that is one reason. That is one thing we're related to the speed we want to operate, right? So you are all very close to there, right? And this is what we are going to learn in this class. I don't expect you guys know about that. You know, actually, I think you know. It's just that you don't know that that is the answer I'm trying to figure out. If you have a lot of input, then you think about how you implement it, right? You have many input. Yeah, even all of them can arrive at the same time. I have n input. What is a function of a LAN gate or inverter? Here I have the so-called pull-up network, right? How do I evaluate? I evaluate by discharging this node, right? Let's say I'm at 5 volt. How do I bring this to 0 volt? I need to discharge the capacitor to 0 charge. And if I have n input, then the resistance is going to be n times m time. So that is a delay. Yeah, many people try to drive me. I'm so relaxed. I don't have to use any force. But the problem is this logic is going to have a train if this is a LAN gate. Then I need to go for a very long train. It takes very long time for me to respond. Then the delay is very long. Yeah. Now, you will know about this later, right? But just start having the mindset that when you see something, don't think that it is that easy as what you see. You really need to understand what is the underlying mechanism. And that is one of the major topics of this class. Okay? Yeah, very good. Thank you very much for helping to answer the question. You guys all get it, right? Any other questions? So after saying so much, then we should know what is an ideal gate, right? Remember, because as an engineer, you always want to know what is the best thing you can do. And then you try to push to that one. And you also try to see if it is worthy, worth the time and money to push to that one, right? So what is an ideal one? Ideal one, of course, this is the VTC of ideal one, right? Can you tell me where is VOH, the output high? I guess you cannot, right? If you can try to annotate on my slide. But I think this one you know, VO high, right? And then this is VO low, correct? And then what is VM? This is Vm at 45 degree, right? And ideal gate is what? I want to have infinite input impedance and 0 output impedance. Now, do you know? This is the output impedance, what I'm talking about. And this output impedance, if it were 0, I can have infinite fan in. Same for here, right? Here is not enough, actually, because they may have resistance. The first student who answered this question was talking about the resistance that will make the signal smaller or delay, right? But then I say, what if it is CMOS, right? So I will also want to have infinite input impedance. I want to have infinite fan out. That would be cool. I can drive anything I want, right? And also I want to make the NMH and NML the same, VDD over 2. This is the VIL. This is VIH. You see they are the same. And both of them equals to VOH over 2. Right? So this is the ideal one. Is that okay for this one? Probably not too difficult, right? And the gain is infinity. Remember when we talk about regenerative property, I say if you have a straight one, cool. You have a very good regenerative property. Right? If you have a horizontal one, oh, then even a little bit noise is going to screw up your whole circuit. Right? The only question is that this is symmetric. NMH equal to NML equal to VDD over 2. Is that the best always? I mean, what I'm trying to say is, can we have a curve like this? Still, everything is very ideal, except that we have this one. If I have a curve like this, right, this is a non-symmetric. Do you think this is a good one? It's an open question. My connection was not stable. Let me repeat. This is a non-symmetric one, right? Why is non-symmetric? Because obviously the NML is smaller than NMH. Do you think this one can be good in some situation, or is always worse than the symmetric one?
Sometimes it could be good.
Can you tell me why?
Because the NMH is larger than the ideal situation.
Okay. So it is symmetric is not always the best. It depends on the circuit. Okay. For example, for the domino logic I just mentioned to you, we actually want to which we call it the dynamic logic. We actually prefer to have a high NML, right? We will explain in the future, but it's easy to understand. What if, let's say, in your environment, you always only have noise when your input is high. You never have noise when your input is low. Then definitely you want to shift this to the left, right? So that you can have, will be more noise immune, right? So this situation can happen. I mean, I cannot say this situation can happen, but what I'm trying to say, you can see that they can, this can justify why it is, it doesn't have to be symmetric to be the best. And then in certain logic, the logic structure itself has no problem if you have a noise when the input is low. It never screw up. But it has a problem when the when the noise is when the input is high, it never screw up. But when the input is low, it can screw up. Okay, and we will revisit this later. Any questions? Now, this is another inverter. This the only thing I want you to, the reason we want to include this is just to reinforce your understanding of all the VTC characteristic. And I think this is in the homework, related to the homework. So I would like you to do it yourself. I'm not going to say here, but again, it just reinforce the understand on what it is VM. Even the curve is so ugly. What is VM? What is noise margin? What is NMH? And what is the VOH? Right? This is VOH, which is VIH. Sorry, and then VOL. Right? So try to play with that. I won't spend time here. Okay. So with that, I want to discuss another quality, right, about propagation delay. Propagation delay, I think all of you did synthesis before or digital logic. You know, they tell you, right? Someone just look at the specifications that the delay of the gate is 1 nanosecond. But in this class, we go into the mechanism underneath. So we want to see what is the cause of the delay and how we measure the delay. Basically, this is an inverter, although it's inverter, but it is the same for other logic, NAND gate, NOR gate. This is V in, this is V out. And you do see that here, when I have V in, okay, V in suddenly go from 0 to high and then go to 0. It doesn't go immediately, right? That will violate the general relativity, right? Signal cannot propagate faster than the speed of light. I cannot just go from V in to V out immediately. It always takes some time. Of course, this is not limited by general relativity. It's just because of the RC delay. So when should we say that the input has settled? So by definition, this is just definition. When you reach 50%, we will say that I received the signal. Before 50%, don't tell me that you have given me the signal. You have given me the signal. Okay, I assume I don't feel it. But at 50%, okay, I feel it. I need to respond. If I respond late, that is my problem, right? So the output will start responding, and then it will start dropping. Even you start responding, you cannot take that for credit. You cannot say I responded already. No, at least you need to finish 50% of the transition. And then the difference between them is the delay. We call it propagation delay, high to low. Means the output go from high to low. Similarly, when your input reduce, I have to increase, right? Output. And similarly, when the input reach 50%, I start counting. And then when I respond by 50% the goal of the target, then I say I complete my response already. And this is from low to high, TPHL and TPLH. So you see for a transit gate, right? It is not symmetric. TPHL doesn't need to be TPLH. But usually we will take the FH and call it the delay and call it TPHL plus TPLH and take their FH, that is the propagation delay. That is sometimes what you got from the data sheet, right? But depends on your application. If your application is only about the general clock frequency, this FH may be good. But if your application really care about the worst case, rising or falling, then you need to look into the individual stuff. Is that okay? Now we also have another two quantity. One is the rising time, TR, and falling time, TF, okay? So the quantity is what? You see that we count when it is 10% of the VDD, right? This is VDD. Or you think about the goal, don't think about VDD, right? You reach 10%, when you start reaching 10%, we start counting. And then when you reach 90% of the goal, then we stop. The difference is the rising time. Anyone want to comment why we don't use 0% and 100%? Right? Why don't I just pick a 0% here and then 100% here? If
so when it is 0%, we can't say the curve is rising, no process. So we can't pick 0%.
Okay.
Only when it is at least more than 0%, here preferably 10%, we can say the curve is starting to rise.
This is also a good answer. But what if I argue, can you take the last 0.0%?
at 0%, the fluctuation in the value is not visible. That is why we prefer 10%.
Oh, that's also a very good argument. Yes. How do you really measure zero, right? 0.001 millivolt, what it is, right? Is it zero or not? So this is a practical concern, right? I did not think as deep as you. And actually, I should not ask about 0%. I should ask about, let's say, for example, 90% or 0% here. This is also 10%. This is also 90%. And the reason I asked the first student, why don't you pick the last one? Now think about this. This is RC delay. Would you reach zero in finite time for RC delay? You won't. You never reach 100% for RC delay. You just get closer and closer. And same for this one, right? But what you are saying is actually the practical reason also, even we can do that, right? So there's no concrete question, right? But actually you injected more thoughts. So you see that based on our discussion, just for the three reasons, one is my reason, two are yours, we should pick something in between, right? So it can be 5% or 95%, just depends on the application, right? But it doesn't matter because this is just a metric to reflect the quality of your gate, right? You make it wider, that's okay, as long as do the same definition for another gate, then I can decide which product to buy, as long as you have a fair comparison. Okay.
And sir?
Yeah.
Do you mean that for the RC circuit, it will never reach like 100%? It's just 99.999, something like this.
Theoretically, right?
Or only t equals infinity, it become 100%. I got it.
Right, right. If t equals infinity, but then it's useless for our definition, right?
Yeah, I got it. Thank you, Professor.
Yeah. That's my fault, but maybe I'm wrong. Actually, I don't know why, but that's my fault. But now just your classmate told me that how do you measure VDD 100%? You have noise, right? It's just not practical and meaningless. And why do we want to give trouble to ourselves? But so that is very good. Okay. So how do we measure the delay of an inverter? For every technology, right? You will say that the delay. You will see that every time you take out a chip, depends on your purpose. If you are really in the foundry or you're doing technology evaluation, you will add something called ring oscillator. What's ring oscillator? It's an odd stage inverter, odd number of stage. Why we want odd number of stage? If this is 0, this will be 1. This will be 0. This will be 1. This will be 0. And then this will be 1. Hey, isn't that contradicting with each other? Then I change it to 1. And then what? And then this becomes 0 again, the second stage, right? So you propagate just like a domino, you keep propagating, and eventually you come back to change me. Then it becomes 1, 0, 1, 0, 1, 0. Oh, and you come back to change me again. That's why it's odd stage. But what is the good thing? You see that because the technology is so fast, nowadays you cannot measure the delay just by probing them. It's talking about picosecond. How can you measure picosecond by a probe? So you will lay out the train maybe for 100 stage, 1,000 stages, right? And then what happened? You see that this one won't switch until you go through everything. How long is the propagation time? This is TP. 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 It means that I switch from, for example, this one, I switch from 1 to, but I would like to 0, right? So I switch from here to half, to here, right? This is the half cycle after NTP, correct? Because I give 0, I don't respond, nothing happened, or you keep propagating. After NTP, you come back to me, and then you make me become 0, right? Of course, this is the whole thing, just an approximation, but it just means that I become this. Then when will I go back to the original state? I need to go through one more time. Then I will go back to 0. So the total time is 2 times TP times N. So if you try to probe it in the oscilloscope, you will see a much lower frequency oscillation. Okay, so for example, right? For example, let's say you do the measurement, right? If T, you find that it is equal to 1 nanosecond. And then you have number of stage equal to 101. Then your propagation delay equals to the T divided by 2N equal to 1 nanosecond divided by 101 times 2, okay, which is about 5 picosecond. Then you can tell your customer, my technology has an inverter delay of 5 picosecond. Is this okay? Right. So the main point is that this ring oscillator is just like the frequency divider. And by the way, people also use frequency divider to do this measurement to find out. No, but this is not a good thing. No, I should not say that, because our goal is to find the delay of inverter, right? For frequency divider, it involves too many logic gates, so that doesn't make sense. What I'm trying to say is, okay, when we tape out the chip, we also add a frequency divider to here. If this is still too fast that we cannot measure, we use frequency divider, then we can measure the frequency divider output. Okay. Any question about this?
Professor, why is that we have to multiply 2? So
that is because
TP should be multiplied by N.
Because it takes one loop to toggle from 0 to 1, another loop to go back to 0. So the period is 2 of this one. The period means you go back to your original state.
Okay.
Yeah, this is the period of this is the period of oscillation. Yeah, good question. This is something we always get confused. Yeah. Now, the only thing I just want you to be very careful when people tell you that my delay of inverter is 20 picosecond. Does it mean that you can operate at a clock frequency corresponding to 20 picosecond? No, right? Because this is just the inverter delay. You are not building your circuit by single inverter everywhere, right? You may have a ALU. Even later we don't learn that, or we will learn a little bit the pipelining. You still cut within each pipe. You still have a LAN gate or a gate. Quite complicated logic, right? So even Intel tell you that I have a 1 picosecond delay for LAN gate, then don't ask them why you are not operating 1 terahertz. We're not, because there's some more complicated object. But this is a good matrix to gauge the process. How good the process is. Is that okay? Now I want to just go back to RC delay, right? Probably you all know just now someone asked, right, why it takes infinity. Just because of this equation. If you have a pulse, right, you take t equal to infinity in order to get to the V in, the VDD.
Hey, Professor.
Yeah.
I have a question about the the clocks. I mean, the last page. For this one, like I know that there's a circuit called phase log loop to provide the clock signal to the chip. And for the digital circuit, what kind of oscillators are they using? Ring oscillator for phase log loop?
Oh yeah, can use different type of oscillator. Yeah, but ring oscillator is one of them. But phase log loop is just this just to generate the oscillation. But phase log loop is that to lock the phase, right? So there are many different type of oscillator. Yeah.
But for instance, like Intel i7 CPU, what kind of oscillator they use? Are they using ring oscillator?
That I really don't know. Yeah, out of my area. We can do a chat. but I don't know exactly what they use.
Okay, okay. Thank you, Professor.
Yeah. Okay, so how do we calculate the delay? Again, this is another method. We calculate the delay when this is 50%, right? Remember? This is the delay. We say 50%, right? So what will happen if it is 50%? So it means V out equal to V divided by 2 equals to 1 plus 1 minus e to power negative, and this is the delay time, right? We divide by this one. Okay, we're just saying that the output reached 50%, right? So now I just do a simple stuff, and then I say, right, this may be VDD. Here is VDD divided by 2, and this is the propagation delay, right? This is one model we can use, right? So if we do this, then you solve the equation, you see that this is just equal to TP equal to log 2 times RC. Tau is RC, by the way, right? I don't go to this anymore because I assume you learned this before. If not, just take it for granted. 1 minus e to the power t divided with tau. Tau is R times C, right? So this is your 0.69 RC. Right? So in the future, for example, if you can find out the equivalent resistance of the inverter and the equivalent capacitance you need to charge, then you know the delay is about 0.69 RC. Okay? Now, so we are getting deeper and deeper using more and more complicated model, right? And then finally, I need to talk about the power dissipation. So there are two types of power, three types, right? But I think you know already. If you have a power as a function of time, right, and then you measure the power, right? The power may be something like this in your circuit, right? This is the FH power. This is power. This is the FH power. And this is the peak power, right? So you have concern when you are based on your circuit design. Instantaneous power is easy, just the V times I at a certain T. We can assume the V is constant. But peak power is the peak one. Why do we care about the peak power as a circuit designer? That is because you draw suddenly, maybe you consume very few power, your circuit, but you suddenly draw a lot of power. The battery might not be able to supply that much of power. And actually that is a problem with my computer. Somehow that if the fan turns on, it will just die suddenly if with my battery. Then I suspect is that the peak power has some problem, right? So there's a limitation of the battery. The battery capacity, we call it capacity, right? So you need to think about that, right? Even your battery has a lot of energy, but it cannot deliver that much of power to you when you suddenly have this surge, right? Another thing is related to the noise and IR drop, right? Here I want to remind you again what I discussed last time. You have VDD, great, but remember you actually have a resistor. And then this is your chip. If you suddenly draw a very large current, this one is going to be VDD minus IR. So if this peak power is so large, it may make your VDD becomes less than the VDD divided by 2 that you want. Then your logic screw up. So peak power is important here, right? Because peak power is related to the peak current. And of course, it's going to generate noise also because your power grid is everywhere. You suddenly have this peak current is going to generate a noise to other circuits. Another is the FH power. You just do an integration, right? I think you probably know that already. The main point is the FH power is related to your heat, right? How much heat you are going to consume. FH power is the one determined, not the peak power. Peak power is just that small amount of time, right? And it also going to determine the heat, the battery lifetime, right? This is not capacity, but it is the lifetime, right? Capacity, lifetime, I'm not saying that how long your battery will not be able to charge again. What I mean is how long it can last after one charge. Okay, peak power actually can hurt the lifetime. Yeah, is that good? Any questions? Now, finally, I want to tell you two matrices to evaluate your technology. One is called power delay product. What does it mean? It actually is talking the gate, the power consumption, of the gate in one switching. Okay, so it is possible that you design a new transistor, a new technology that you consume very few energy. However, it takes very long time. Then how should I compare? Which product should I buy? Right? You come to me say that, oh, I really conserve energy. Right? Why don't you buy me? I use very few power, but actually your computation never finish. Then I would rather buy the other guys, right? So that's why when you compare the technology, you will multiply the delay time times the FH power, and power times time basically is just energy consumption per operation. This is called power delay product. But that is not good enough, because sometimes you can really make this energy very low. But although you already captured the time, but it still takes very long time to compute. So a better matrix is energy delay product. It's the energy times the delay. So basically, it's just the power delay product further times the delay. Okay, so you have these two matrices. Right? Think about that, and usually we will use this EDP, right? And when you read the paper, pay attention to that. But not always we want to use EDP, right? Sometimes we care about PDP more, right? Again, this is some matrix. Matrix means a simplification of a more complex picture, right? So for example, subthreshold circuit. Subthreshold circuit is that we operate all the device at the off state, right? Not really off state. If you put a log scale of the current as a function of VG, you will see this. This is VTH. Below VTH, I have very low power consumption, but I still can operate it. It has orders of magnitude different when I turn on the VG and turn off the VG, right? So for this type of circuit, we care more about the PDP, power delay product, right? So it really depends. Is that okay? Any questions? Now, although I missed many pages, but these are just process fabrication. I can go over quickly for 15 minutes for the rest in the next lecture. But I think it's good to explain this. Otherwise, I think it's 4:15 already. You are feel free to go. I will stay for more time.